This is the phase 2 of the project. The team here will present the key learnings and the work that we have done. So for this project, we have here Intel Flex, Modex 3D, Celanese, Incidix, FIT loads, Afino, Acrometrics participated, in fact, including the phase 1 and 2. We have 2 project chairs and also a program chair. Besides this project on the socket Warpage, we have another project work on the package Warpage. So Vicky Low is the program chair on the study on the Warpage challenges. Myself is Hailei Fu from iNEMI. I facilitate the project. Next slide. So here are the team members who are the major contributor to this project. Besides the names here, we also have others within the project, the company. They support the experiments and some other works. Next. So for the project chairs, we have Chongken Oi from Intel. He is the senior staff technology development engineer. He has been with Lenovo for, Intel for over 20 years. His major experience is in thermal, mechanical, and flux analysis in the electronic packaging assembly process development, and also the thermal management. We have a co-chair, Wenli Xu from Celanese. Wenli is the design and CAE manager. He has a background on the material engineering. Is experienced in the mode flow simulation and the design, the simulation tools and the engineering. So with that, I will pass to Tongken to introduce today's agenda, and also the other major team members will present the work together with Chongken. Chongken, go ahead.
Yeah, thanks, Hailei. Hi, everyone. I'm Chongken from Intel. So this is the agenda that we have for today. So I'm going to touch base about the project introductions and the objectives. Then later we're going to share the LCD socket manufacturing process, material property overview, then modeling material and methodology. So these other sections will be taken care by the team member, right? So next, please. So before we jump into phase 2 in details, right? So we'd like to recap for phase 1 summary. So far, we have completed the phase 1, right? So in the phase 1, we have actually validated the filling stage of this liquid crystal polymer or the LCD material, right? So in the phase 1, we have done the validation, and also we have simplified the pinhole geometry, right? As you can see, we have original model at the bottom, the graph there, right? Then simplify model 1, simplify model 2. So we're able to simplify the geometry and run with the faster time while achieve a similar accuracy. So these are the 2 major key learning that we achieved in phase 1. Okay, next slide, please. So now talk about the phase 2 background and the objective. So as you know, socket is to use to mount the CPU to the motherboard, right? So as we see that there's an increasing in the trend in the pin count number, and hence this also increase the socket size of form factor. And also for the larger socket form factor, it imposed a significant challenge in the warpage control during the assembly before process, right? And then we have the 3 objectives that we are studying in phase 2. So the first objective is to characterize liquid crystal polymer or LCP, right? Anisotropic mechanical property for Mori-Tanaka model. So Mori-Tanaka model is a new model that we investigate in the phase 2, right? It could be used as alternate options as compared to our baseline model. And the second objective is to quantify room temperature and high temperature dynamic warpage prediction accuracy of this Mori-Tanaka model compared to the baseline or the composite model. And the third one is to evaluate socket warpage measurement methodology and recommendation. Okay, next. So this is the overall project framework, right? So you can see that we have two major phases. Right? The first one is strategy definition, planning, and proof of concept. And the second stage is the new model evaluations, improvement, and validation stage. Right. So this project started with project strategy definition. So we identify the socket dynamic voltage prediction gap, right? And we plan for the alternative model. Then later on, we proceed with the NDA agreement between MODEX and Celanese. So this particularly talk about the LCP resin anisotropic property, right? So after we attain the NDA agreement, then we proceed with the anisotropic mechanical property measurements and characterizations. Then after that, we have conduct a first POC by using a back coupon. So at least we would like to have first cut information or data to tell us how it is a new model compared to the composite model. So after we get back coupon learning, so we proceed to the next phase, which is an actual test vehicle build. So the test vehicle build here is actually referred to the socket. So for this socket build, actually we introduce two variations, right? The POR and the core out. And also we introduce three LCP grades or material options, right? So we like to introduce these more options so that we would like to study the variations of this new model as compared to the baseline. So in the dynamic warpage measurement and validation, so we look into both room temp and high temp. And also we define the measurement method by follow the GenX format. Then the second improvement also come into the place, right, after we done the dynamic warpage measurement for the socket is we talk about how to incorporate this CLTE or the coefficients of linear thermal expansions into the model. Right, so my team member will talk more into detail later on, right, how we incorporate a CLTE pre-TG, CLTE post-TG, and CLTE average. So these are the three options that we investigated. And we will come with a recommendation which is the best option to proceed for this model. So by the way, TG is the glass transition temperature, right? Then finally, we define what is the output metrics for our benchmark. So we are comparing the two metrics, right, inclusive of two socket design and three LCP grades. So basically, we look into the modeling versus empirical dynamic warpage comparison as a first key metrics. Then the modeling versus empirical for both room temp and high temp correlations. So we are using these two key metrics to complete the benchmark. So, and finally, the EOP webinar. So after we're done, so we will share as for today, and we will put out the key learning and the recommendations. Okay, so this is basically the overall framework of phase 2. So the next one, I would like to invite my team member, Roger, to talk about the socket assembly process overview. Thanks.
Thank you, Ken. This is Roger from FIT, and I'll be introducing about how we make the sockets. As you can see on the right part, it is a heating device where we want to melt our plastic pellets. The plastic pellets is actually a tiny boat, and it will be melted with a high temperature, and then it will be ready in the hopper. While heating it, we want to check that in this air there's no moisture air inside. We want to put to make sure that it is 100% plastic pellets only. Next page, please. While introducing about the heating device, this is all the settings that we by making sure that it is in the best conditions, including the cylinder temperatures and the mold temperatures. And we also set the injection speed to make sure that the sockets don't break easy, and exactly with the pressures as well. Next page, please. This is the detail of how we made the sockets. First of all, we're clamping it inside the cylinder. So actually, when it's melting, we want to make sure that the cylinder is full of the plastics. And the yellow part is the model we made for the sockets. After that, we want to inject uh, the the plastics inside the moldings, and it will make the shape for the sockets. Well, the developing part is where we are done with the injections, and we want to make sure that there's no anything else in the cylinders. We want to make sure that the plastic is all inside the motor. And next step is easy. It's cooling. After the heating, it's very hot, so we want to make sure that um, the sockets don't break easier, and the sockets will be in a good shape. The motor opening is where we prepare to push up, as well as the injections. Then we drop the sockets, and that's how we make the sockets. Next page, please. Um, talking about the sockets, we have to introduce our cap, contact, and solder belt as well. The cap is for the sockets that after we made the sockets done, we don't want any dust on it. So we made another cap to make sure that all the contacts are insured. The contact is where we contact with the CPU pad, and the solder ball is on the PCB. Next page, please. And this is the process for the socket. First, we want to insert the contact, the golden part, and that shows in the figure 2 is the contact, and we'll be inserting it into the socket itself. After that, we'll be applying the flux, and then put the solder balls on the back of the socket, and we'll be going to the RL machine where the solder ball will be stick in on the sockets itself. After all of this, we'll be doing the high pot test. The high pot test is where we check that if the contacts or the solder balls are in the right place. If it's not, then we'll be picking it up. After everything is checked, we will have the assemble cap on the top of the socket to make sure there's no dust on it. After that, we'll be packaging everything. Next page, please. The rest I will be giving to Wendy. Thank you.
Thanks, Roger. Hey, hello everyone. This part, let's have an overview of LCP material properties. LCP is the short name of liquid crystal polymer. Comparing with others, comparing with semi-crystalline polymer, LCP shows nematic structure both in solid and liquid phase. And this leads to a high chain continuity and then very high mechanical properties and also good other properties. LCP has a very good thermal resistance, and its DTUL temperature can go up to 340 degrees C. Based on that, it can work for that free solderable process. Regarding to the molding ability, it has super good flow ability on the proper shear and still without flash issues because it's with the low heat of fusion. It's really a very good material candidate for those thin wall with complex geometry like the high density CPU socket. Besides this, it is inherently flame retardant with very good chemical resistance and is the best class barrier to oxygen and moisture. Last, it can contain reinforcement like fiber, mineral, and other fillers, which can reduce the anisotropy, which offers good space for compounding development. Next page. And for CPU socket, the flowability, SMT eligibility, dimension precision, and stability are the top 3 critical requirements. Comparing with other polymers listed here like PPS, PPA, LCP has much better flowability. Additionally, it has the lowest risk of flash thanks to its lower heat of fusion. This results in very short cycle time. In aspect of thermal resistance, it has the highest HDT temperature among the typical high heat polymers. Because of the volume change from liquid phase to solid phase is minimum, so LCP leads to excellent dimension precision. In the working environment, LCP has a lower CLTE and also lower water absorption. Then these two factors lead to the very good dimensional stability. Next page. For this study, 3 LCP grades were selected, considering the flowability, warpage resistance, especially that after SMT, and also taking into account the weld line stuffiness, which is important during stitching. They are, at the left picture, they are vector E for 88I, vector fit 30, and then at fit 145L. The prior two grades are fiber and mineral reinforced, while the last one is only fiber reinforced. Please refer to the figure for more detailed properties. For recent years, the HDI socket with much bigger size and more pins, more material solutions were developed in Celanese. If any needs and interest, please contact us. Next page. Okay, very special for LCP. Polymer and resin has an isotropic already. To incorporate this into simulation, anisotropic tensor modulus and CLTE were measured based on on-field resin. To obtain anisotropic tensor modulus, quasi-static strength string testing were finished on cut specimens with orientations. As the left picture, specimens were cut from a rectangular plaque. Orientations were 0, 45, and 90 degree to flow direction. The gorge area were all in the same location. For anisotropic CLTE, like the right picture, samples were cut and measured both from an injection molded ISO 527 tensor bar and a rectangular plaque to evaluate differences. For this study, that either option resulted in similar results. Finally, CLTE were given based on the software specific requirement for temperature range. Okay, thanks. Then hand over to Felix.
Okay, thanks, Wendy. So next page. Okay, so this is Philip from Model 3D. Okay, Model 3D was founded with providing plastic injection molding simulation solution for the plastic industry. So our vision is to helping customers to make good plastic product. And with our own material center, research center, Model 3D provides the material characterization service to consider material property that require in the simulation. And for the semiconductor field, Model 3D IC packaging provides the flow analysis of the encapsulation process from filling, curing, cooling, and warpage to advance the manufacturing demands such as wide swap, die shift, filler concentration, post-thermal curing, stress distribution, or the structural evaluation. And we also developed a diverse solution for different solution process simulations such as the transfer molding, conversion molding, capillary under field, and the electronic parting. Next. So in this project, model design 3D is used to simulate the injection molding of the failed circuit and predict the dynamic warpage through the thermal treatment. Two types of the circuit, the POR and the core design, are selected for the validation purpose. On the core design, through and the blind hole are intentionally created in the specific area to alter the plastic flow pattern and the feeder orientation in the molded circuit to decrease the trouble and the defect of the injection molding and the warpage. So all the simulation model is generated based on the tool design for the mold trial. You can see there are 4 cavities in one mold with a harmonic system and 2 harmonic drops connect to column. But in the mold trial, only 1 cavity is available, and the 2-point tuner gates are used for the cavity. And the 3 distinct LCP material are used for the validation. All the 3 materials are fiber reinforced plastics, so not only the temperature and the pressure, but also the fiber orientation information from the fitting analysis is necessary to precisely predict the warpage of the molded circuit. Next. So after the standard injection molding simulation, we perform the leading analysis for the validation with thermal deformation measurements result. The molded circuit was shown to be exposed to a controlled environment temperature history based on the thermal deformation measurement. And the temperature distribution of circuit was calculated at each time step and the warpage predicted at the desired temperature point. Then the surface shape and the flatness of the dead bar side of the circuit were estimated and compared with the measurement result. Next. So to calculate the warpage of fiber reinforced plastic product, generally the simulation tool will ask user to input the mechanical property of plastic such as modulus and CLT under the condition which all fibers are aligned in the same direction. Then the mechanical property can be transferred to the condition with different fiber orientation probability for each mesh element. In this project, 2 methods to input the mechanical property of fiber reinforced plastic are used in the validation. The first one is measuring. We can measure the mechanical property of composite sample and directly input the data. And this is the most used method since everyone can characterize the material if they have the ability to make the sample follow some measuring standards. The left chart is a sample of the input by the composite model. You can see the fiber and the polymer base are treated as a whole and show the strong anisotropic in different directions. And the second general used method is we can characterize the fiber, the mechanical property of fiber and the polymer base separately, and we input the data and combine with the composite model, like with the theoretical model such as Mori-Tanaka model. The right chart is a sample of the input by the Mori-Tanaka model. Here we can see both the polymer base and the fiber are assumed isotropy. However, due to the fiber shape, we offer the anisotropy when they are combined into the composite. Okay, next.
Hello everyone, I am Pierre Toussaint from Incidix. Please go to next slide, please. So let me just briefly introduce Incidix. Incidix is a company which is providing some of Warpage methodology for different fields like semicon, telecom, automotive, power electronics, aerospace and defense. We do provide like some equipment which allow to perform warpage measurement on sample by heating them and measuring at different temperatures the warpages. Next slide, please. Next, please. Thank you. So Intelix is providing like TDM equipment, which are basically like composed in two parts. One part is a 3D sensor, which has imaging capabilities. This is like a projector and a camera combined together, which allow to take some 3D measurement of whatever is inside an oven. It can be like small sample from 10 by 10 mm up to 600 by 600 millimeters square. And it can provide like warpage and CT measurement. The sample are being put into a chamber, which has some like thermal capabilities. They are being heated up from the top and bottom with a slope up to 6 degrees C per sec and a temperature range from -65 to 400 degrees C. So the point is to be able to simulate any reflow, SMT, or other types, and to check the warpage at different temperatures. Next slide. Thank you. So there are different applications where the tool can be used, such as like package warpage measurement. So we can measure up to 30, 40 different packages during a reflow. We can see in the photo here, the shape variation between room temperature, 30 degrees C, then 240 degrees C, and then back at 30 degrees C. So we can see the shape evolution. And also we have the warpage graph that allow to characterize the different samples. We can also measure like a larger sample, such as strip, and get like the full strip shape or one single unit shape by just changing the length extension. During the same profile, we can get both information. We can measure more complex samples, such as like BGA with ball, for instance, and we can capture the ball and the substrate all together. Then our software is able to, I would say, mask the ball area to get only the substrate warpage, or mask substrate to get the ball warpage. We can have PCB, we can have wafers, and different other samples. Thank you. Next slide, please. So for our subject, we have been measuring like the different design and material for the sockets, and being able to compare them. So they will measure like 9 by 9 through a thermal profile 25 degrees C up to 245 or 250 degrees C, then back to 25 degrees C. And we were able to capture like the full socket shape, and then we were just masking the area which are not good for the analysis, just to get like the ROI and the 3D shape of each socket at each temperature. Next slide, please. So we provide two types of information. The first type is absolute warpage, which is a real 3D shape at different temperatures. So you can see at the left part, like the image number 0 is the shape at 22.9 degrees C. We have 334 microns. And we can see in red and white the higher part, in blue and black the lower part of the shape. And then we can see the shape evolution through the thermal profile. So it's getting flatter, and then when we cool down back to room temperature, we recover like shape slightly similar to the initial shape, a little bit more warped. We have another type of information you can provide, which is the relative warpage. In fact, the reason why we provide two types of information is because when we need to compare different samples altogether, we may have like different warpages at room temperature. So while comparing during thermal profiles different samples, we might not know if the difference is due to the initial shape, which is different, but the trend being the same, or that the behavior of each sample as regard to the thermal profile is being different. So relative warpage allows to annulate, to make the initial shape considered as 0, and we just check the shape variation of each sample as regard to room temperature. Next slide, please. So we have been measuring the different design, different material, and getting the absolute and relative warpage. So on the left graph, we can see that, well, the different sockets are showing like different warpage values at room temperature, the far left point. And we can see the evolution that during the heating process, the warpage is decreasing, and during the cooling process, the warpage increased back. But if we need to compare all of them all together, it's kind of difficult. If we check on the relative warpage at the right graph, we can see that if we just not consider the initial shape, or we just consider the shape variation of each sample as regard to its initial shape, we can see that all the sockets are showing a warpage increase during the heating process and decrease after a while in the cooling. And some sample are showing a very like similar shape or like low relative warpage, which means that when it comes back to room temperature, we recover more or less initial shape. Although like the blue one, lot 30, are showing some variation, like some permanent change, I would say. Next slide, please. So this was the result for the warpage, and now I will hand over to Philip. Thank you very much.
Okay, thank you. So next page. Okay, so before we start our main target of circuit, the geometry of the coupon was selected for tester validation. So here two runner design are used. One is the center gate with gate at the middle of the coupon, and the side gate with gate at the one end of the coupon. And all the simulation are performed by Model 3D 2024 version, and with the standard 5-layer boundary layer mesh part and heads-up-based runner mesh. Next page. Okay, also the environmental temperature profile are set according to the experiment data, and the surface shape and the flatness of the planar side of coupon were estimated and compared with the experimental result at the given temperature points. Next. Okay. So when we compare to the experimental result, both the center gate and the side gate show that the general mesh standards are not good enough for this project validation. Here we see the light blue curve is the right plot. In the right plot is the dynamic warpage predicted by the standard mesh. And we see the flatness at the room temperature is not bad compared to the experiment, but we find that at the high temperature, we highly underestimate the flat warpage value. So we do the mesh convergence test by decrease element size and increase the total elements number. The mesh clipping resolution are shown in the left chart. And from the convergence test, the results shown in the right side plot. The upper plot was the dynamic warpage of the center gate model, and the lower one are the side gate model. And we can see the flatness increased significantly when we decrease the mesh size, and it converges to the value very close to the experimental result. We also find that the convergence mode are a little bit different between the center gate model and the side model. Also, the flatness of the room temperature increases as we increase the mesh size, but it is much smaller compared to the increase with the flatness at the high temperature. Next page. However, even we find a reliable mesh for validation with the mesh convergence test. When we compare with the experimental result, the experimental results show some characteristics that are difficult to explain. So in this page, we can see the dynamic warpage of the two gate design and the free material grade. The solid curve indicates the experimental data from 3 different samples, and the dark line and the hollow square represent the simulation result. The simulation results show flatness proportional to the temperature, and the flatness change when cooled down to room temperature due to the stress release. However, the experimental results show the maximum flatness occurred before the coupon was heated to the maximum temperature, and the warpage quickly deformed to the upside direction, and the negative flat is even stronger than the magnitude before the coupon is heated. So we suppose there are some condition or some criteria happen in the experiment, or the some physical model such as the nonlinear effect that what happened and not considered in our simulation now. So we decided move to our main target of circuit validation. Next. Okay, next page. So next we talk about the circuit validation results. So we first examine the general user method input by composite. So here the results show the warpage at room temperature of 2 circuit model and the 3 LCP grade. The left plot of each set is the predicted surface shape, and the right plot is the measured surface shape from the thermal deformation measurement. So we can see the predicted surface shape matches with the measured sample in all the sets. But we also find that the magnitude underestimated compared to the measured value. Next. Okay, so here is the dynamic warpage shift. A similar trend was observed for the high temperature warpage shift for the composite model. Here, the 2 solid lines represent the measurement data from experiment, and the dark line represent the modeling predicted by composite model. The overall dynamic warp trend predicted was in good comparison with the experiment. The surface shape shift from one type at room temperature to another when it heated to the high temperature. But composite model consistently underestimate warpage value at each set temperature point. For the underestimated value are different from the material and the circuit design. Next. Okay, so why does the composite model underestimate the warpage value? The final warpage shape is a combination of different effects such as temperature and pressure. And for the fiber reinforced plate, generally the isotropic due to the fiber orientation is one of the most important effects. So here we separate the total disment into fiber orientation effect due to the fiber orientation, and the random fiber orientation effect due to the temperature and the pressure, to help us distinguish which effect is the most dominant. So in the result, the fiber orientation effect in the result, the fiber orientation effect show the same shape and even higher magnitude than total disment, as the random fiber orientation effect show upside warpage direction and small magnitude compared to the total length. This indicates the anisotropic due to the fiber orientation dominate the circuit warpage shape and magnitude. And the composite model underestimates the warpage magnitude may be due to we underestimate the anisotropic effect of the LCP. Next page. So why does the input by composite model underestimate the isotropy of plastic. The benefit of input by composite model is that the material can easily be characterized by measuring the molded sample. However, we know that the fiber in molded sample is highly aligned near the surface, but more random in the middle of thickness. Input with the measured data with the sample as full aligned data will always due to cause the underestimate of the isotropic effect for the simulation. So there are some methods that can calibrate this issue based on the data input by composite. And we already know that it works well for general plastic, which is the polymer base is isotropic. However, the pure LCP itself has a strong anisotropy. So we need to try other method to overcome this issue. Next page. So here we use another method. The input of the fiber and the liquid crystal polymer properties separated. And here we also extend the isotropic polymer base general use for injection molding to an isotropic polymer base to match the characteristic of the pure LCP. Next page. So here is the dynamic warpage comparison. The hollow green diamond presented the result from input by Mori-Tanaka model, and we can see the result from Mori-Tanaka model are relatively close to measurement result compared to the result by composite model for POR design. And for the core design, it is a little bit worse. The dynamic warpage evolution changes is due to overall composite property different from the two input method. Next page. Okay, so another factor that may cause the warpage prediction variation is the GLT calculation method. For injection molding simulation, generally the CLT is measured by the TNA and average up to the gas transition temperature. However, the slope of measured dimension change show an upward turning after the gas temperature for LCP as shown in the plot. So if we use the general CLT standard to simulate the warpage and even the leading up to 260 degrees, this will cause the prediction accuracy issue. So to verify the CLT effect, 3 different CLT value calculation approaches has been investigated. The CLT pre-TG means the CLT value by average expansion change from minima measured temperature to gas temperature. And the CLT post-TG means the CLT value by average expansion change from gas temperature to the maximum measured temperature. And the CLT average means the CLT value by average expansion change over all measured temperature range. Next. So the effect of different CLT calculation option for room temperature warpage is shown in this page. All 3 CLT calculation options provide the same warpage shape as compared to measured data, but different in the magnitude for all the for the 3 LCP and the POR design. The warpage predicted by the CLT pre-TG is much lower than the measured data. And the warpage by CLT post-TG is contrary almost twice the measured data. Meanwhile, the warpage by CLT average, which was about a 20% variation as compared to measured data. And the CLT average have the most closer results. Next. Okay, so similar results shown with the core design. The warpage predicted by the CLT pre-TG is much lower than measured, and the CLT pulsar TG encountered almost twice the measured data. And the CLT average, the most closer as compared to the experiment. Next. So the effect of CLT calculation upstream to dynamic warpage is shown. The hollow triangle presented the predicted by CLT pulsar TG, and the orange circle was the result by CLT average. The absolute magnitude of dynamic warpage has shifted depending on CLT upstream. Warpage magnitude predict through both the CLT pre-TG and the CLT post-TG method result in either under predict or over predict scenario. CLT average improved dynamic warpage predict at the room temperature and high temperature with the POR design. And in the core design, the prediction improved at room temperature, but not in every case at a high temperature. Okay. So here the thermal correlation analysis was conducted to assess the accuracy of the purpose molding model for various LCP material in both POR and core design under room temperature and high temperature condition. A room temperature warpage correlation comparison for various modeling methods is shown in the left plot. The composite model recorded the weakest correlation with measured data. For correlation with Mori-Tanaka model, CLT pre-TG and CLT post-TG method record a good correlation of 0.886 and 0.873 respectively. CLT average method record the best room temperature warpage correlation of 0.932. In general, the CLT post-TG over-predict the warpage magnitude, meanwhile other methods under-predict it for all three LCP materials investigated in this study. A similar correlation comparison for high-temperature warpage prediction is shown in the right plot. The composite model shows a relatively good correlation, but its warpage magnitude was underestimated as discussed earlier. And the CLT pre-TG method show a good correlation of 0.887 and very similar to the room temperature correlation value. However, observed a weak or no correlation signal for CLT post-TG method. Finally, the CLT average approach record a good correlation of 0.886 with measured data. CLT average method is recommended based on high correlation obtained from both room temperature and high temperature warpage comparison. Next. Okay.
Thanks, Philip, for the good sharing on the result and the discussions. So now I'm going to close the summary, right, for this phase 2 project. So so far, what has been shared and investigated with this new model, the Mori-Tanaka models. So we have compared and validate against the dynamic warpage with the measurements. And also, we also investigated this new model with the CLTE average input method, and is found to provide a good correlation for both room temp and high temp warpage data. So couple this new Mori-Tanaka model and the CLTE average approach, we're able to obtain a good correlation, which means R squared is greater or equal to 0.88 with the measurement data. And again, there's a future recommendations, right? So I think in the future, right, if we could incorporate the full CLT versus temperature as a table input into the model, that will increase the prediction accuracy, right? Currently, the workaround is to use a CRT average approach. And the second one is to further validate the model result with larger form factor socket, and also consider the effect of various core design. So this also will help us to further quantify and the accuracy of this new Mori-Tanaka model. Right. So, yep. So now the next one is a Q&A sessions. Yeah. So I think is any question from the audience, right? Then we are here to answer. Yeah.
Okay, thank you, Chongken and the team. So any questions, we open the floor for discussion. You can either input through the Q&A or chat, or just unmute yourself to comment. So any questions from audience? Or any additional comments, remarks from the team?
Haley, just an additional comments to share with the audience. So on top of this, at the end of the project webinar, right? So the work of this is to also publish in the 2024 iNEMI conference, right? That was organized a few months ago in Malaysia. Yeah.
Yes, we do have a paper and presentation published. If you are a member of iNEMI, you should be able to access from the iNEMI website. Or you can go to the IEEE Explorer, the portal, to get a download. So for the socket warpage study, it's not within the industry, not many studies in this area, but I think the team has done a great job to explore the possibilities and understand the impact of the different properties, and even how to improve the model to get the more accurate or results, and to reduce the computing time. That's the focus from the phase 1.